Welcome to our next lecture of Mechanics of Material. This is Salman, Assistant Professor, Department of Mechanical Engineering, ISL Engineering College. So last class we have discussed about the composite material, in which you have seen that how the deformation is going to happen when composite material, which is nothing but when two materials are merged together. The very first condition which we discussed in composite materials is the load will be distributed among the various materials, and the deformation is going to be equal. So today we are going to see another problem which is related to composite materials. So the problem is given as above, that is 3 bars made of copper, zinc and aluminum are of equal lengths. So clearly they have mentioned there are equal lengths, having cross sections is nothing but the areas of cross section, 500, 700 and 1000 meters mm square respectively. They are rigidly connected to their ends. They are being connected rigidly at their ends. If this compound member is subjected to an axial pull-off, means here there is an axial pull-off 250 kilonewton, and estimate the proportional of load carried by each material. So they are asking how much load is the each material going to be carried. Okay, and they have given the values of E for copper, zinc and aluminum. So let us take the given data. So the lengths are equal, so I am making it length of copper is equal to length of zinc is equal to length of aluminum. Next, the area of cross section of each every material is given in a respective way. So take it as copper AC is equal to 500 mm square, AZ is equal to 700, AL is equal to 1000, and the axial pull or the total load is given as 250 kilonewtons. Okay, so we have already discussed that in a composite material we have to apply for two conditions. So I am trying to apply the first condition. In a composite bar, we know that the total load should be distributed between the two materials or three materials which are being used in a composite material. Here in composite bars, they have used three materials together. You can take this composite as an example of your cement pillars, okay, in which you have concrete, you have steel rods, you have cement, you have sand, you have stones. So all they have mixed together and made one material. Similarly, this material has been made. So PT is equal to P1 plus P2, which is nothing but the load acting on material 1, load acting on material 2. Here there are three materials, so I are taking it as PC plus PZ plus PL because there are three materials. We know that PC is nothing but load is equal to stress into area. Load is equal to stress into area. Or we know that stress is equal to stress sigma is equal to, just a second, I will try to highlight the words so that you can able to analyze easily. So PT is equal to sigma into A. We know that sigma into A from stress is equal to load upon area. From there we can calculate the values of load. Okay, so I am trying to highlight this. So PT is equal to sigma C into AC plus sigma Z into AZ plus sigma AL into AL. Okay, so this is the first condition which you are going to obtain because of the loads. The second condition, we know that the deflection of all the materials should be equal. Means if one material extends, another material should decrease the same amount, because overall expansion will be same or overall deformation should be same. For example, if you see in a pillar, if steel rods are coming out when the temperature is increased from the material, then the whole structure will be failed. So in composite material, this is one of the important thing. The deflection of the individual material should be always equal to one another. So you know that deflection delta L is nothing but PL by AE. From that I am going to apply PC LC by AC EC for this material, which is equal to PZ LZ by AZ EZ. Similarly here PL AL by AL EL, where C represents your copper, Z represents your zinc, AL represents your aluminum. So instead of solving all together, I am taking two together. First I am taking these two options. Okay, so PC LC by AC EC and PZ AZ LZ by AZ EZ. where we know that LZ and LC are equal, because the initial cases they have clearly given that the lengths are equal, so you can strike out the lengths. So the left out things is PC AC EC by PZ AZ EZ. We know that A values are given. A for copper is 500, AZ for zinc is 700, whereas copper's Young's modulus is given. Young's modulus for zinc is given. Substitute all the values, we will get a relationship between PC and PZ. Similarly, do it for PZ and AL. PZ and AL, or you can do for this two or this two, anything. But you should get all the relationships in terms of a single number. Here we have got PC is equal to PZ. So instead of doing PC and PL, try to do PZ and AL, because it will be easy for you. Okay. First, this all are converted in terms of Z. All are converted in terms of Z. So PZ LZ by AZ EZ is equal to PL AL by. So in this, again the lengths are equal as given in the problem. So substitute the values. Substitute the values of AZ. AZ is 700. EZ is given as 1 into 10 to the power of 5. PL is equal to 1000. E is given as 0.8 into 10 to the power of 5. 10 to the power of 5, 10 to the power of 5 cancel. This is 700. This is 1000. So we are substituting the values and we are going to get the relationship of PAL in terms of PZ. If you see here also PZ, here also PZ. Okay. Now let us go back to the condition 1. What is condition 1? Condition 1 is PT is equal to PC plus PZ plus PAL. Clear? So from here I am going to substitute in the place of PC, we can substitute the value of 0.93 PZ. In the place of PAL, we can substitute the value of 1.14 PZ. So among all these three, if you see, the PZ is common out. So I am taking it common out, where 0.93 plus 1 plus 1.4. So we are going to get the value as 3.07 PZ. The total is 3.07 PZ, and the total load is given as 250 into 10 to the power of 5, 10 to the power of 3, as given in the problem. Okay. So this should be equal to this value. Then you are going to get the value of PZ by doing the calculation. Once you get the value of PZ, you can directly substitute in this formulas. 0.93 into PZ, 1.14 into PZ. You can able to get the values of PC and PAL. PC and PAL. Once you get these values, you can able to identify your sigma Z, sigma C, sigma L. What is sigma? Sigma is nothing but PZ into AZ. What is PZ? PZ is your load, AZ is your cross sectional area. Multiply these two things, you are going to get the values of stress. If you see the problem, in the problem they have told us to find the individual proportions of the load. That is nothing but the ratios of the load, which we have already calculated, and they have told us to find the induced stresses. So we have identified both the things. With this we can able to complete the problem. Clear? If you have any doubts, you can ask in the comment box after the completion of class. So next question is same question, and in the composite bar I am giving you more and more questions in this composite bar, because the chances of asking the question from the composite bar is very much high. Okay, these are repeatedly asked questions. Okay, in your big questions like 10 marks questions or 7 marks questions. So the two vertical rods, one of steel and another of copper, are each rigidly fixed at the top and 50 centimeter apart. So here first thing you have to understand the question properly. Two vertical rods. Yes, there are two vertical rods, and another one of copper, another of steel. One of steel, another of copper. Each rigidly fixed. Both are rigidly fixed at the top. Till here one question is completed, and 50 centimeter apart means both the rods are at a distance of 50 centimeter to one another. Okay, they are 50 centimeter apart like this. The distance between these two rods is 50. Now both are rigidly fixed from up and down. Clear? Next, the diameter and the length of each rod are 2 and 4 centimeter. Both rods are 2 centimeter. Both rods are 4 meter long. So here diameter is same, length is same. A cross section fixed to the rod at the lower end. Okay. So next, what they are doing, they are connecting a crossbar. Just like I can draw the here. So there are two bars like this. So to the two bars which are at 50 meters apart, they are taking a block like this, crossbar, which is trying to hold this. So to this crossbar they are making a load of 5000 newtons, such that the bar remains horizontal after loading. Because even after loading it is remaining horizontal, means the elongation of this and the elongation of this should be equal. If this elongates more, what happens? The bar will become like this. If this is elongating more, okay, because this elongation is more, here it is less. If this elongates more, what happens? This will elongate like this, the crossbar will become like this. This is having less elongation, means both the rods should be elongate same. Okay, find the stress in each rod and the position of load and the positions of load. So where this load should be acting, this 5000 Newton, where it should act in this 50 centimeter length, either it should act below this or below this, where it should act, so that you should not get the deviation of the crossbar. You should not get the deviation of the crossbar. That is their aim. So first of all, you have to calculate the values of this piece. What are the loads induced in, or what are the loads acting in each rod? Then you can able to identify by doing simple mechanics. That is nothing but by taking out the moment at any point, either in a copper rod or in a steel rod, you can able to identify the things where the load should be made concentrated. This is simple mechanics problem which you have done in your engineering mechanics. So let us try to take the given data. The given data is like this. DS diameter is 2 centimeter, diameter of copper is 2 centimeter. Here they have given in terms of centimeter. Try to convert all in terms of mm. If the all units are same, no need to change. If different units are there, try to change all of them in terms of mm. We have already discussed the conversions in the previous classes. So ds is equal to 2 centimeters, dc is equal to 2 centimeters, whereas length of rod is 4 meters. So 1 meter is equal to 1000 mm. So again 1000. Copper is equal to, copper is also same. So the rods are 50 centimeter apart. This is also given in terms of centimeter. Try to convert it into millimeters. Now load they have given it as 5000 newtons, and they have given ES, that is nothing but Young's modulus of steel and copper, as 2 into 10 to the power of 5, 1 into 10 to the power of 5 Newton per mm square. Okay. Now what I am trying to do is I am taking the composite bar condition. The very first condition is PT is equal to PS plus PC. Obviously this condition is given, and the second condition is this: delta L of copper should be equal to delta L of steel. So with this you will get the relationship between PS and PC. So I am applying this. Delta L, you already know delta L is equal to PL by AE. Okay, delta L is nothing but the deflection or the elongation or deformation of the bar. PS into LS by AS into ES, where PC is equal to PC, LC, AC, EC. Okay, this is the formula. We are again and again using this. Okay, remember this formula every time. So delta L is equal to PL by AE. Why we are giving these suffixes are nothing but because these suffixes are for the particular material. Okay, so here lengths are same, so this can be cancelled, and how the areas are same is nothing but, since they have given the diameter, area is equal to pi by 4 d square. So both the diameters are same, means you can able to make the areas also same. You can able to cancel the areas. So ES by EC. ES value we have given it at 2 into 10 to the power of 5. EC's value is given as 9 to 10 to the power of 5. Here again 10 to the power of 5, 10 to the power of 5 cancel. PC is equal to 2, sorry, PS is equal to 2 PC we have got. So again take this value in your first condition, that is the load condition. PT is equal to 2 PC plus PS. So in PS place, in the place of PS, we can substitute the value as 2 PC. You can check the equation, first equation, PT is equal to PS. So in the place of PS, we can able to substitute 2 PC, 2 PC plus PC. So here 2 PC plus 1 PC is nothing but 3 PC. So from here you can calculate the value of PC, and similarly you can calculate the value of PS. This can be done by 2 ways. So that is, first is 1667 into 3 you can do, sorry, into 2 you can do, or you can directly take it as 5000 minus, you can do whatever you want. You use basic mathematical calculation, you can able to find the values of this. Now what is the position where this 5000 should be acting, that how we are going to find is, we will try to do a simple mechanics like this. We know that there is some load here, we know there is some another load here, and we have a distance between them as 50 centimeter. In between these two I have to place a load like this. Okay, so where the position is like this, I will try to take the moment about this point, or I will try to take the moment about this point. Any one point I have to take. So I am taking the moment from this load. Okay, consider this load a distance as x. So taking the moment about this point, so I am considering this is as my steel, this is as my copper. Now I know the values of the load acting in the copper, and that load will be acting upward and this load is acting downward. Obvious, because the summation should be same. So if this load is acting downward, means these two loads should be acting upward, then only your equilibrium condition can be achieved. Okay, so 5000 into x, about this point 5000 into x should be equal to PC into what is the distance between these two is 50. That is, we have already converted in terms of mm as 500. Okay, PC into 500. From here we can calculate the value of x, which is found to be 166.67 millimeter. In terms of millimeter, it is 166.67. Similarly, what is the distance from the other end? So what is the total distance? 500. So from 500, if you can subtract this x value, which is nothing but your 166.67, you can able to find the position of other rod. Okay, clear? Done. So next topic we are going to discuss is thermal stresses in composite bar. So first of all, let us understand what is thermal stresses. For example, you might be seeing in a normal days, or you can see that when you walk on a railway track, you will be finding a small gap between these two, and between these two they will be having a clamp which is try to hold this two railway tracks or railway line. So why this actually a small gap is given? So what happens in thermal stresses is, generally the material will be able to expand when there is a change in temperature. Similarly, the material is having a property basing upon the coefficient of thermal expansion, that is nothing but alpha. It can able to contract or it can able to increase. So generally, without application of some load, if you are previously we have been discussing the case where you are having a bar, to this bar we are applying a tensile load or compressive load, either to expand the rod or to compress the rod. If there is this load is also not there, if there is some change in temperature, then also the bar can able to expand. So because of this expansion, there is some amount of stress generated inside the material. When the bar is trying to expand like this, when it is trying to expand, to avoid this expansion, there will be some internal resistive forces generated. That stresses are called as thermal stresses. And now how we are going to calculate the deflection because of thermal stresses is this formula. Previously we used PL by AE, here we are going to use alpha into L into delta T. What is this delta T? Is nothing but change in temperature. How far the temperature is going to be changed. If you are changing from 0 to 100, the deflection will be of different type. If you are changing from 1 to 10, then it will be of different. Okay, so the very most important thing here is change in temperature. The next thing is the length of material, how big length the material you are using. Next is type of material, that is decided by the coefficient of thermal expansion. Okay, so if this small gap is not provided in the railway track, what happens generally is, when summer condition comes, this will try to expand. Okay, if this gap is not provided, they will try to merge like this, and they will be creating a bulge like this. They will try to move one above the other. So because when the train comes, when the train passes through, when they are bulged out, the train may become detraining of the train will happen if this is the case. Because of that, we give some provision for it to expand. Similarly, if you see in your electric lines, electric poles, between the electric poles, the wire will be somewhat hanging like this. You can think why they are making the lines hanging instead of making the lines to be tightened like this, instead of making the two wires to be tightly fixed between the two light posts. Why they are giving this hanging is nothing but the copper is having a good thermal expansion, especially in terms of winter it can expand. Similarly, under winter condition it will become tightened. Initially itself you have become tightened them. When they become too much tight, the electric wire will break. In winter season it is having a chance of breaking. Okay, so when they break, because these are live currents, live wires, someone may be hurt when the live wire falls down. Similarly, if you are making it to hang too much, so it can even touch the ground. So to avoid that, they will make you only a small curvature, so that in winter it can able to get a contract. Okay, in electric wires the provision is given for contraction. In railway trains it is given provision for expansion. Okay, clear? So this is thermal stresses. Now because of some thermal stresses, there are some changes happening. When stress is there, obviously there will be some amount of strain. We know the relationship between the stress and strain. We know that stress is equal to delta L by L, or strain is equal to delta L by L. You have already known the value of delta L. What is delta L? Alpha L into delta T. L value is here, so L will get cancelled. E is strain can be written as alpha into delta T. Alpha into delta T. Similarly, when you know the value of E, we know that E is equal to sigma E, or sigma is equal to, we know that stress sigma is equal to, or you know the values of Young's modulus, sigma by stress by strain is equal to Young's modulus. Stress by strain is equal to Young's modulus. From this you can able to calculate the value of stress. Stress is equal to E into E. You know the value of strain, alpha into delta T. Substitute, you can able to calculate the values of thermal stresses. This stress is not a tensile stress or not a compression stress. This is called as thermal stresses. This is called as thermal stresses. Clear? So let us see a basic problem based upon thermal stresses. A rod is 2 meters long at a temperature of, here the most probably when the temperature is given, you have to compulsory go for a thermal expansion problems only. A rod is 2 meters long at a temperature of 10 degrees. Find the expansion of rod when the temperature is raised to, from 10 degrees the temperature is being changed to 80 degrees. If the expansion is prevented, means they are not allowing the expansion to happen. When it is being prevented from both the sides, obviously there will be some amount of stresses generated inside the material. So what are the stresses which are induced when you are preventing this expansion? We have to calculate. Okay, so let us take the given data. So they have given the length of the rod as 2 meters. We will be taking 2000 mm. Since we know that 1 meter is equal to 1000 mm. Initial temperature is given as 10 degrees, final temperature is given as 80 degrees. So Young's modulus is given as 1 into 10 to the power of 5 Newton, mega Newton per mm square. See here they have given m. So we know that what is mega. We have already discussed this unit conversion in our first lectures. 1 mega is nothing but 10 to the power of 6. Here again meter square is given. Again 1 meter square we know 10 to the power of 6 mm square. I will try to change 10 to the power of 6 mm square. So this 10 to the power of 6, this 10 to the power of 6 will be cancelled. Okay, here I have cancelled it. So what is left out? E is equal to 1 into 10 to the power of 5 Newton per mm square. Why I am converting these units in terms of mm square is nothing but your initial units are in terms of mm. Okay. Now thermal expansion is given as alpha is equal to 0.0012 with respect to per degree centigrade. So we know that the stress or the strain, the delta L value, we know that delta L is equal to L into alpha into delta T. We try to calculate the value of delta L first, how much expansion it is going to happen. What is the delta L here? Nothing but already we have discussed change in temperature. So with respect to the change in temperature, it is going to expand by a length of 1.68. With respect to this, how much stress is generated in the material? So we know that stress is equal to E strain. Stress is equal to E strain. So stress sigma is equal to E into alpha into delta T. E into alpha into delta T. E value have calculated 1 into 10 to the power of 5. alpha value is given in the problem 0.00112. So this will be most probably given in your problem. Delta T is given. You can calculate the values of stress induced. Clear? So next problem, we are going to the next problem, in which composite bars are there. Composite bars is nothing but there are 2 to 3 materials are present. In this, there is a case of happening both thermal stresses. If the loads are not given, it will only undergo because of thermal expansion. If there is some load, it can even go thermal expansion as well as the expansion because of the load. That is called as superposition condition. So initially we will see the composite bars because of thermal expansion alone. With this we can able to stop today's lecture. Okay, a flat steel bar 200 mm, 20 mm, 8 mm is placed. So they have given 200 mm, 20 mm and 8 mm. So length, thickness and breadth of each material is given. Okay, is placed between 2 aluminum bars of. So this is for steel bar, 200 mm length, 20 mm wide, 8 mm thick steel bar. Is placed between 2 aluminum. Is placed between means above the steel bar there is some aluminum, below it also having aluminum, and the thickness of aluminum is 6, but whereas for steel it is 8 mm. So I have drawn the figure here. Okay, all the bars are fastened together at the room temperature. So they are kept initially at a room temperature. Find the stresses in each bar when the temperature of the whole assembly is expanded, is raised to 50 degrees centigrade. Assume the Young's modulus of steel is given, aluminum is given, coefficient of expansion of steel and bar are given. So first condition what we have to see is, what is this case? This case is purely a composite bar case, correct? Composite bar case with respect to what we say. Sorry for the inconvenience, just a second. So composite bar case with thermal expansion. So first of all, I will write down all the data which they have given. I have write down all the data here. You see 200 gigapascal is given. So giga means 10 to the power of 9. I have written 10 to the power of meter square is given 10 to the power of 6 mm square. With respect to that, we are going to get the value of 10 to the power of 9. Okay, you have been seeing all these things. You should not have any doubt regarding this. Since no external force is acting on a composite bar, the elongation is purely due to thermal expansion. Very, very important thing. Okay. So in thermal expansion, materials alpha, the material whose alpha is more, that material will undergo large amount of expansion compared to that of the material whose alpha value is less. Because what is the value of, what is delta L formula? Delta L is equal to L into alpha into delta T. What is the formula? Delta L is equal to L into alpha into delta T. So alpha is directly proportional to elongation. If the alpha value is more, the expansion will be more, obviously. So here, whose alpha value is more? If you see the question, so the alpha value of aluminum is more. The alpha value of aluminum is more. Here you can see it is 24, this is 12. So obviously this is more value. Because of that, it will expand more. So whereas the other rod, this expands more and this expands less. So this is happening uneven. So to avoid this, there will be a what should be acting, or what is the induced stresses inside the material. Since it is trying to expand more, there will be induced stress, compression stress acting on this material and this material, which tries to compress. Similarly for steel bar, it tries to expand. The induced stress will try to expand, so that the overall expansion will remain same, and finally the material will become as a even material. So here, what is the compression force acting on the aluminum should be equal to tension force acting on the steel bar. That's what you have written here. Since force compression on the aluminum should be equal to force of tension acting on the steel. When I say force, we know that force is equal to stress into area. That is stress into area. So with this, we are going to get a value of relationship between the two stresses. Here the very most important thing again we have to see is, here there are two aluminum bars. So while calculating or while taking the area stress induced here, the area here you have to take double. Why? Means area A is equal to, here also we are having area, here also we are having area. 2 into B into T. Why we are taking B into T is nothing but the stress acting will be on this direction. Okay, so this cross section it is acting. What is this length we have taken? 20 mm. What is the thickness of the material is 6 mm. That's why I have taken 20 into 6, not the length. Thus, if the load is acting like this, then we have to take the length as well as the thickness. But whereas the load is acting like this here, because of that we have to take 20 into 6 and we get the relationship between this. Now the total strain of the material is ES plus E alpha. Total strain in the material is ES plus E alpha. That is nothing but this strain happening here. If you see, this is expanding and this is contracting, or this is more expansion, this is less expansion. Okay, so that is the reason here alpha is taken as positive and whereas this is taken as negative. So ES is ES plus EAL is nothing but ES E alpha is expanding, this is less expansion. So we know that ES is nothing but sigma S by ES. This is your strain formula. Strain is nothing but sigma by E by T into alpha A minus alpha S. So we substitute, we got the relationship between sigma S and sigma A. We use the relationship. Okay, we substitute the EA and ES values. We have given the values of alpha and temperature difference. We substitute all the values. We are going to get, here I am taking 1.5 sigma A. With respect to that, sigma A is common out here. So with that you can able to find the values of sigma A. Once you get the value of sigma A, you can able to calculate the value of sigma S. Clear? So with this we can able to stop our today's lecture. So in next lecture we will be discussing the further topics like superposition, thermal stresses in composite bar, as well as the superposition conditioning. So this we will be going to discuss with the after that. So first unit is a very big unit, you have to have some patience in this. So after that we will be continuing with our first lecture. First unit continues. Okay.